The campus was on lockdown. That is correct. But me being me, with the power of connections, I can still be on campus. Although my connections is just those web option people. I contacted a web option coordinator, and then he hooked me up with one of these rooms for web option purposes. And well, can't complain. It's still better than me at home with my crappy blackboard on my wall. So we will go with that. So today, we just finished handing in A4. So technically, I am allowed, because now everybody handing their assignment at the exact same time. I am actually allowed to give out answers for A4. Although, truth be told, I think I've given out most of the answers for A4 before you had the opportunity to hand in. So technically, you already should know the answer for A4. Mostly just problem for A4. The only thing that is hard is question 3. Question 3 is the only question that is difficult. Everything else is just incredibly trivial. So for A, 3A, where the range of S is within the kernel of T, that question, again, you trace through, you take an arbitrary element from the input of T, and then you just trace through this entire function. And then once you reach T of S of something, you get 0, right? And everything after that will just be 0, because linear transformation maps 0 to 0. And then for B, you show two transformations with a kernel of dimension 3 or higher, and then add together, suddenly become the kernel of the dimension of the kernel suddenly become 1. Just find counterexamples to that. Pretty trivial. Vector spaces, prove that it is a subspace. I do not want to prove that because it is too much work. Prove that it does not. Why is the lecture stand like this? Prove that there does not exist a linear map from R5 to R5 where the range equals to the kernel. Well, if you look at the rank equation, the dimension of the domain equals to rank plus the nullity, right? The rank is the dimension of the range, and the nullity is the dimension of the kernel. Well, the dimension of the domain is 5. So that means the rank and the nullity cannot be the same, because you cannot have 2.5 dimension of a rank and 2.5 dimension of a nullity. They have to be different. 1 is 2, 1 is 3, 1 is 4, 1 is 1, 1 is 5, 1 is 0, something like that. So they cannot be equal, right? And then you have the range and kernel of already in different dimension. If they're in different dimension, then they cannot be the same, right? And an example of a linear map that go from R4 to R4 is you're just trying to map the range to kernel. So maybe your range is your first 2 element, and then your kernel is also your first 2 element, where you just map the first 2 elements to 0, right? 3D already did in previous tutorials. 3E. Okay, you know what? Let's do 3E again. And then we'll move on to determinant. So this is the proof of isomorphism, first isomorphism theorem. Right? So we're given a couple of things. All right? We're given a couple of things. We're given T going from V to W, a linear map. Right? And it is also the first time that Kaidi, Kaidi in previous lecture, first time used the word homomorphism. Right? So we're given that T is a linear map. then we're saying that the following map, which the assignment call it T tilde. I do not like that notation. Although, I mean, it is pretty common notation. I do not like that. I'm just going to name it phi. That map from V slash the kernel of T to the range of T is isomorphic. So how do we do this map? We take one element from V slash kernel of T. So that will be a random vector V plus the kernel of T, right? And then we just simply map it to T of V. So this is isomorphic. So a couple of things that we need to prove. So the first thing that we need to prove. The first thing we need to prove, or actually the zeroth thing that we need to prove, is well-definedness. We need to make sure, we need to first make sure that this is a map to begin with, right? If it is not a map, it cannot be a linear map, right? So we need to first make sure it is a map to begin with. Okay. So how do we prove it is well-defined? So if we want to prove something is well-defined, we need to make sure a single value only gets mapped to a single value. It does not get mapped to multiple values, right? So similar to a vertical line, every single input has exactly one output. So basically, we want to show, right, if A plus kernel of T equals to, I don't have enough space on this line. So if A plus kernel of T equals to B plus kernel of T, right, then T of, and then the result of this mapping, which is T of A, equals to T of B. Right? Because if we put these two into phi right here, if we plug A plus kernel of T into phi, we get T of A. If we plug in P plus kernel of phi, plus kernel of phi, plus kernel of T into phi, then we get T of B. And we want to make sure that their result is also equal, so that if we have a single element as an input, we do not get two different answers, right? A and B are vectors, yes. So A plus kernel of T and also B plus kernel of T are from V slash kernel of T. Right, so you know that both A and B are vectors. Yeah, the quality is okay. So we have this. Okay, so let's just prove it. So this is an implication, so let's just prove it directly. Okay, so prove. We're gonna let A plus kernel of T, B plus kernel of T, coming from the domain, be arbitrary. And A plus kernel of T equals to B plus kernel of T. Okay, so we're going to assume the first part, and we need to show that this, the first part, implies the second part. The first part implies the second part. So we're going to choose two random elements from the domain, which is V slash kernel of T, such that these two are equal. Okay. Now, what does that mean? Well, A plus kernel of T equals to B plus kernel of T. What does this mean? This implies A minus B is in kernel of T. Right? So this is a property of the quotient space or the affine sets. Right? If two affine sets are equal, that means their difference is in the subspace. This is important. Right? Just because A plus kernel of T equals to B plus kernel of T, it does not necessarily mean A equals to B. That is not true. The only thing that is true is that A minus B is inside kernel of T. So this is important. Okay. So what does that mean? That means T of A minus B equals to 0 because A minus B is in the kernel, right? And everything in kernel gets mapped to 0. And because T is linear, T of A minus T of B is 0. Which implies TA equals to TB. So it is well defined. So this is your part 0. This is like expanding everything out. Although technically, if you just write this line, this line, this line, this line, I guess it's enough, but it's probably a good idea to just write everything out. Right, so any questions regarding part 0? If it is not well defined, that means that it's not even a function to begin with. Right, so we say that a function is well defined. We say that a function is well defined, right? So that at every single location, it gives us an exact value, a single value, right? If you look at this function right here, at this location x, we have 3 different values here, right? So I give you the input x, and I ask you, okay, I give you the input x, what is the output? And you tell me, oh, it's one of these 3 values. I don't know exactly which one of these 3 values is. Well, then it is not really well defined, isn't it? Because I gave you the input, you have no idea what the output is. It's one of the 3, but which one is it? No clue, right? So similarly, if I have A plus kernel of T equals to B of kernel of T plus kernel of T equal, but their output is not equal, that means if I plug in a single value, I can either get T of A or T of B. I don't know which one I'm going to get. Right? You can get any one of the other with some probability attached to it. But what is that probability? Right? You don't know exactly what you're getting out. So that is not well defined. So well defined means single input, single output. Single input means a unique single output. Exactly one output. Okay, second part is linearity. Again, we want to prove that this is isomorphic. You first have to prove that it is linear to begin with. If it is not a linear map, well, what does it mean for something that is not linear to be isomorphic? Right, so I have to prove it is linear. Quite simple. So let A plus kernel of T, B plus kernel of T. So let's pick 2 random elements from the domain. Okay. And we have to pick a constant as well. So constant in this case, this is a vector space. This is a vector space over the exact same field as V. So these 2 right here, same field. Right, so let's call that F. Going to pick a random constant. So let R be in F. a random constant. So I have two arbitrary elements from the domain, and I have constant from the associated field of the domain. Now let's see what happens if we take phi of A plus kernel of T plus R times B plus kernel of T. Right? Let's see what does this equals to. Well, the property of the affine set tells us if we take the affine set and we multiply it by a constant, then that's the same as just multiplying a constant to the representative. Right? We do nothing to the set itself. We just multiply by the representative. So this is the same as phi of A plus kernel of T plus RB plus kernel of T. Right? If I take a coset and multiply by some constant, I just multiply the representative. Because if I take this entire set, which by the way is a subspace, and I multiply by a constant, then I didn't do anything because the subspace is extending in all directions, right? So it is contained in a scalar multiplication. Right? And also, if I add two cosets together, if I add two of them together, am I blocking too much of the view? I don't know. I'm fat. Maybe that's the problem. So if I add these two cosets together, again, I mean, I can say that I add kernel of T to kernel of T and I get two kernel of T, but two kernel of T is still just kernel of T, right? So the addition does nothing to the set, but all it does is adding the representatives together. So I have A plus kernel of T plus RB plus kernel of T. Then adding these together is the same as just adding the representatives together. So this equals to phi of A plus RB plus kernel of T. Right? Yeah, fairly visible. Now, what is phi of this? Well, phi of V plus kernel of T is just T of V, right? So all I did is I take the representative and I slap it in T. That's all I do for phi. So in this case, it's the same. I'm going to take the representative, I'm going to slap it in T. So this equals to T of A plus RB, right? Which we know equals to T of A plus R T of B. Because again, T is linear. This is given. T is a linear map. It is a homomorphism. It is a linear map. It is given here. So we can just use this fact. It is linear. So we know T is linear, right? So that means, so what is T of A? T of A is just going to be phi of A plus kernel of T. Well, this does not help at all. I wish I had a chair with a wheel. I wish I had a wheelchair. Plus R phi of B plus kernel of T. Right, which would mean it is linear. So that means linear. I have every single sound turned off, which is why I do not hear you. But if you want to talk, just unmute your mic and talk. We have like 10 people in the room. It's not going to get too messy. You can just unmute your mic and I can hear you. Pretty sure I can.
Jerry? Jerry? Can you hear me? Jerry, can you hear me?
All right. Maybe not. Why can I not hear?
Hello?
Why can I not adjust my volume either? Blackboard.
Can anybody else hear me?
It's a piece of garbage. I'm so glad that we get rid of Blackboard.
Well, that's weird. Okay.
Blackboard
Maybe
Collaborate is
something with
going to
the
be here
headphones.
to just haunt us till the end of the day. Audio, speaker volume. Do I have sound?
Hello? Because I want to ask that question that we all texted about, because that's kind of important. It might be specific to quotient space, but I'm not sure.
Oh, now I can hear you. Can you repeat
Hello?
your question? Yes.
Yeah. So we were asking why, I'm not sure where it was, but why, oh, for linearity, why did you say A plus kernel of T and B plus kernel of T belong to V divided by kernel of T instead of just saying A and B are arbitrary values and just V?
Well, because we're trying to prove the linearity of phi. We're trying to prove the linearity of phi, right? It has nothing to do with T. T has something to do with V, which is if I'm trying to prove the linearity of T, I would get A and B from V. But right now I'm trying to prove the linearity of phi. That means I have to get two arbitrary elements from here.
Which means that it has to be from there, and it has to be in that form for quotient space specifically?
Yes, it has to be in
Okay.
this form because every element in this domain is in this form.
All right, thank you.
No problem. So that concludes linearity. Well-defined linearity. Splendid. You can still see after I erase it, right? Yeah, that's fine. It's okay. Everything's gonna be all right. Except the final exam, but everything else is gonna be all right. Okay. So now you have to prove injectivity. Now I have to prove injectivity, right? I don't know why I keep on writing my Y's like J. Injectivity. So I want to prove injectivity. All right, so there are a couple of ways that I can go with proving injectivity. The easiest one to prove is we want to show, right, that the kernel of phi contains only the zero element. So there's only one element that it contains, and it is a zero element. So this is what we want to show, right? Now, let's start with the left-hand side. Let's consider what kernel of phi is. What is kernel of phi? Well, kernel of phi is all of the elements in the domain, so all of the V plus kernel of T's. So all of the elements in the domain, right here, that gets mapped to 0, such that phi of V plus kernel of T equals to 0, right? So we're looking at all of the elements in the domain, that gets mapped to 0, right here. Okay. Now, what does phi of v plus kernel of t equals to? What does this equals to? Well, this equals to t of v, right? Phi of v plus kernel of t equals to t of v. So phi of v plus kernel of t equals to 0 is the same as t of v equals to 0. What does it mean for t of v equals to 0? Well, t of v equals to 0, what does that mean? That means, oh, v is in the kernel of t. Right? Because everything in the kernel gets mapped to 0. V gets mapped to 0. That means v must be a member of kernel of t. Oh, but if v is in the kernel of t, what does v plus kernel of t equals to? Well, v inside kernel of t means v plus kernel of t must be 0 plus kernel of t, right? Because of the property that if I have v in S, right, then v plus S is just the same as 0 plus S. In this case, I have v plus kernel of t, but v is in kernel of t. So this just simply equals to 0 plus kernel of t. Right? So this will prove injectivity. So the only thing in the kernel of phi is the trivial solution. It's a trivial 0 element because 0 always gets mapped to 0. Right? So you know that kernel always contains 0. Now you just want to know that the kernel only contains 0. It does not contain anything else. Right? Okay. And then for surjectivity, my handwriting is awful. So for surjectivity, well, for surjectivity, we want to make sure that everything in the range, everything in the codomain is in the range, right? So everything in the codomain is mapped from something from the domain. Everything in the codomain is the result of some map from the domain. So we want to prove something about everything in the codomain. We want to prove a property about everything in the codomain. How do we do that? Well, if I want to prove something about everything, I have to just pick an arbitrary element. So let W in the range of T be arbitrary. Right? I pick an arbitrary element. If I can prove something for the arbitrary element, then I can prove that for every single element. Right? So I pick something from the codomain, arbitrarily pick something from the codomain, and I want to prove it is indeed the result of phi of something from the domain. Well, if W is in a range of T, what does that mean? W is in a range of T. W is in a range of T means it is the result of some mapping of T. So W is the result of some mapping of T. So T of something, let's see, of V, right? And because T maps from V to W, and we know that W is in range of T, that means this V must be from the vector space. Must be from the vector space V, right? W in the range of T, it is the result of some mapping in terms of T, and what input does T take? Some element from the vector space big V, right? So that means W equals to what? Equals to, well, T of V. T of V. T of V is just phi of V plus kernel of T, right? And we know that V is in V. Right? These two are equivalent because of this. We know that small v, right here, this one, we know that this element is in big V. What does that mean? Well, since, well, I shouldn't write an arrow here. So since small v is in vector space big V, right? Therefore, the small v here is in big V. That means the small v plus kernel of T is indeed in this quotient space right here. Is indeed in this quotient space right here. So therefore, V plus kernel of T is in the domain. And this will prove surjectivity. Everything in the domain is mapped from something. Sorry, everything from the codomain is mapped from something in the domain. Right? And this is the reason why it is in the domain, because of this one right here. And it's very important for you to know for a fact that V is in big V. Why is that? Because T maps big V to W. Right? So the input of T is vectors from vector space V. Okay, questions? And then of course you put everything together, 0, 1, 2, 3. You just glue everything together, you get a complete proof of sorry, put all four of the pieces together, you get the fact that it is isomorphic, because you know it is well defined, it is a linear map, it is injective, and it is surjective. Right? So that means it is isomorphic. So for 3E, part 4, all you have to do is write a single sentence conclusion. Or I mean, if in part 4 we did not prove well-definedness, then in part 4 we should prove well-definedness. No, that small v in big V means V kernel of T is in V slash kernel of T. Right? Small v in big V means V plus kernel of T is in this quotient space right here. Right? And phi, the domain of phi, is this quotient space. So all I proved is everything in the codomain is the result of some mapping phi of some element in domain, which is basically what the definition of onto is, right? Surjective. Any other questions? Yeah. If not, I'm going to move on to assignment number 5. By the way, it is so much easier than assignment number 4. Which is so much easier. Well, yes, if you know pretty well what determinant is, you understand how you calculate eigenvalues and eigenvectors and stuff like that. It is actually pretty easy. What's the answer for assignment 5? So for example, for the first question, yeah. I just look at the first question for 2 seconds, I can immediately tell what that determinant is. It's not hard. like as long as you know what that determinant is, as long as you know what determinant means, it's pretty simple. Two minutes, now 2 seconds, to be honest. Because, so for Q5, 1, I'll just give you a Q5, whoops. For A5, so I'll give you a couple of hints for every single question for at least the first part. So for determinant, pretty simple. So for Q1, you can consider the hint is the fact that determinant of A does not equals to 0 means A is isomorphic. This is something that we do know, right? If the determinant is non-zero, that means A is isomorphic. Well, if A is isomorphic, that means A of x plus y equals to AX plus AY. But x and y are linearly, x, y, z are linearly independent. How does that work? So this is hint for 1. For 2, well, for 2, just 2 is just laughably easy. So this determinant of A equals to determinant of AB equals to determinant of A and determinant of B. This is something that you do know, and also determinant of A inverse equals to 1 over the determinant of A. Do you need to compute any determinant? No, you don't have to. Literally just use these properties, you get an answer. That's Q3. Oh, that's question 2. Oh, what a discovery. 2, 3. Okay, question 1 is just whatever, nobody cares. Yes, data was a problem. I'm rebooting. Give me a second. Okay, yes. Okay, so Q4. Well, consider the determinant of A equals to the determinant of A transpose. If you have a skew symmetric matrix, what does A transpose equals to? Consider that, right? And also use the fact that determinant of C times A equals to C to the power of N times determinant of A. Right? So this is another property. So question 1, 2, 3, 4. In order to see the answer, all you have to do is to Google. But all of these are on Wikipedia. Right? So with these properties, you should be able to solve question 1, 2, 3, 4 incredibly easily. No problem, right? No problem. Well, you don't on your assignment, you do not have to prove these properties because these are in lecture. So you do not need to prove them. You can just take them for granted. But you still need to show me how does these properties imply the answer that you gave me, right? You do not need to to derive these properties yourself, but you need to show me whether this property gave you the answer, right? You cannot just say, oh, Jerry says the answer is 5 and expect full mark. Nah. Even if I mark it, it'll still be 0. Right, so this is for question 1 to 4. For question, so this is on the determinant. So the Q5 determinant. For, what was the other thing that I was thinking of? Okay, we can talk. We need to talk a little bit about eigenvalues and eigenvectors because they are a little bit difficult and they are a little bit annoying. Ooh, I need more water. Okay, so yeah, we talk a little bit more about eigenvalues and eigenvectors. As I said, this assignment is actually pretty easy. We don't need to worry about it that much. You do not need to worry about it that much. If you actually know what you're doing, this entire thing shouldn't take you more than a single hour to do. Okay, let's see. Eigenvalues. I'll use the wrong end of the chalk. And eigenvectors. Eigenvalues and eigenvectors. What do they mean? How do you calculate them? Although how do you calculate them, Kaidi already did talk about it. It's pretty much nothing. Okay. You just subtract lambda I, and then you do stuff with it. So, why it is important to talk about eigenvalues? What is it important to talk about vectors, right? So, might it make sense to first talk about what does eigen mean? Eigen, that is an interesting prefix there. It is not English as well. I think that is pretty obvious. Eigen came from, I believe, German. Eigen came from German. I think it means characteristic, or it means the proper. What we're looking at is, remember that every single matrix, every single n by n matrix represents some kind of linear transformation. Remember that. So we have maybe, from R2 to R2, originally we had a rectangle, right? And then under some linear transformation A, what do we get? Well, maybe instead of a rectangle, we get a parallelogram. It's a linear transformation, right? Although the arrow should make it all the way across. Like that. Right? So every single matrix represents some kind of linear transformation. This is something that we established in the previous chapters. Well, that kind of makes sense in terms of people who are interested in computer graphics, right? Or any kind of lighting things, or the new words like ray tracing, whatever. And it makes sense to talk about, well, after the linear transformation, what did not change? Because not everything changed, right? For example, this vector here did not change at all, right? And for this vector here, all we really did, well, I kind of just moved it a little bit. The direction, in terms of the direction, it did not change at all, right? But every other vector did change directions. These two, the vectors on the top and the vectors on the bottom, did not change directions at all. But the vectors that are going diagonally, or that is going perpendicularly, did change, right? And any other vector also changed. So we look at these two vectors and see what is so special about them. These two vectors did not change directions at all. So these two vectors under this linear transformation would be considered the eigenvectors. The vectors that does not change directions after a linear transformation. The vectors that does not change directions after a linear transformation. This chalk is supposed to have no dust. False advertisement. Okay. And in terms of things like projection, like if I have some kind of higher dimensional object and I want to project it down to a lower dimensional object, then it also makes sense to talk about, well, which one of these vectors that compose of this object did not change, right? What is invariant under a linear transformation? So eigenvectors is an invariant in terms of direction. Should I say is? Are invariant in terms of direction, right? After linear transformation. Right? And not every single one of them have, vectors that does not change directions. There are linear transformations that obviously have vectors that does not change directions, and there are linear transformations where every single vector changes directions. Right? So for example, if I have a triangle, right, and I apply a linear transformation, but my linear transformation is a rotation. What do you remember about the rotational matrices? They're beautiful, aren't they? Then obviously every single one of these vectors, right, they're going to change directions. Right? The first vector, vector 1, vector 1, vector 2. Where do they come from? Well, this is vector 1 before, and this is vector 2 before. Right? Obviously every single vector has changed directions because you rotated the entire plane. There's no vector that left untouched except the origin, of course. But the origin isn't really a vector, which is why in terms of vector spaces, in terms of eigenvectors, we never really count to 0. We don't learn anything from 0. Right? And again, the only thing that we care about is the direction. Right? We do not care about length. The length can be stretched or it can be smaller. We don't care about it. The most important part in terms of linear algebra is mostly about directions, right? And it kind of makes sense. Like later on, when you learn more about linear algebra, you'll see that we almost never talk about norms because nobody cares. The length of a vector, what does that do? Something, right? It's mostly just used to calculate the angles, cosines. That's what you use the norms for, right? And no, we cannot. So the question was, can we find, does it make sense to talk about eigenvectors when we're talking about linear transformation that changes dimensions? Generally speaking, no, it does not really make too much sense to talk about it. Like if you go from R3 to R3, but the result is R2, that is fine. So like if I have, you have something R3, right? And I have maybe let's say a sphere here. So I have a sphere here, right? And under the linear transformation, I get a circle on R2. I get the shadow of it on R2. So this is a linear transformation. Did it really change dimension? Well, if you still count this circle as an object in R3, so if this is X, this is Y, this is Z, for this circle, you just have elements like, some X, some Y, but Z equals to 0. You didn't really change the dimension because you're still talking about it in the third dimension, right? However, if you say that I'm going to map this to the second dimension, then no, it does not make sense to talk about eigenvectors anymore. So in this case, we can still talk about a couple eigenvectors. So maybe a vector on the top and the bottom of the sphere going in some directions. Well, it is still the same within a circle, right? It will be still in the section within the circle. But there are other vectors that just gets collapsed down to 0. That also work, right? But if I say I have something like a sphere, I have a sphere, right? And then I map it to R2. So I mapped it to a circle in R2. Which vector is which? What is the before vector? What is the after vector? And in the same direction. Well, does the vector 1, 1, 0 and the vector 1, 1, do they have the same direction? It doesn't make any sense to talk about it anymore, right? We only know whether or not if they have the same direction, whether or not if their angle between them is 0 or 180, right? Or pi. I'm sorry, I should not use degree. That is a sin that I just committed. But for a vector in R3 and a vector in R2, we can't really compute the angle between them. Right? We don't know what the angle between them is, and we don't know which vector goes to which vector. Like, how do you know that if this vector is the same as this vector? Are they the same? You don't know. They're from different dimensions, right? Entirely different vector spaces. So it only makes sense to talk about eigenvectors when it is a linear map from one dimension to the exact same dimension, right? Or I mean, most of the time it's just one vector space back to itself. Most of the time we just talk about one vector space back to itself. Okay. So that is that. Okay. So how do we compute eigenvectors? Well, based on our theorem, based on our not theorem, but based on intuition, what does it mean when we talk about eigenvectors? We're talking about eigenvectors such that after a linear transformation, the direction does not change. What does that mean? That means if I have a vector v and I apply a linear transformation A, the result is going to still have the exact same direction. But then again, we do not care whether or not if the length or the norm of the vector is stretched or not. We don't care about that. So as long as the direction stays the same, the length can be whatever it is. We don't care about it. Right? So this is the one that we're looking for. We're looking for all these. This would be an eigenvector. We're looking for all v's such that after the transformation, it is still in the same direction, albeit with some change in the norm. And if we rearrange it a little bit, we have AV minus lambda v equals to 0. Well, recall lambda v, what is this equals to? Well, this equals to lambda times v1, v2, so on all the way to vn, right? And this is actually also equivalent to lambda 0, lambda 0, 0, lambda times v1, v2, all the way to vn. Right, it is also equivalent to talk about it this way. These are the same. If I multiply by some constant to a vector, that's the same as just multiplying with the identity matrix to that vector. Right, so this is A minus lambda I times V, which equals to 0. Well, we're looking for this to equals to 0. Well, if A minus lambda I does not result, how should I phrase it? This is another matrix right here. This is another matrix right here, right? And the only way that we can get this matrix to multiply by V and get 0 in the end is that this matrix cannot be invertible. Because if this matrix is invertible, that means it represents an isomorphism, right? Then the only vector that gets mapped to 0 is 0, because kernel equals to 0. Kernel only contains 0, right? So we do not want this matrix to have non-zero determinant, because if it is non-zero, again, it has an isomorphism. So for non-trivial solutions, right? So for non-trivial solutions, and non-trivial solutions has a specific meaning. It's not just me insulting you guys, saying everything is trivial. So i.e., V does not equals to 0. For non-trivial solutions, we want this matrix to be non-invertible. We want this minus lambda I to be singular. Singular, right? Or the same as we want the determinant of A minus lambda I to equals to 0. This is the reason why this equation down here represents the way that you calculate eigenvalues. This is the reason. Right? So this is the reason why the determinant of A minus lambda I equals to 0 gives you what lambdas are. And based on what lambdas are, we can calculate what lambda B's are. So let's do a couple of examples. Oh, and the lambda here, I forgot. This is an eigenvalue. So let's do a couple of examples that we all are familiar with. Will lambda be the diagonal? And no. Lambda is still calculated through the determinant one with our characteristic polynomial quadruple or something like that. We can worry about that later. So let's look at a couple of examples. Okay. So the first one is the scaling matrix. All right, so A equals to some C 0, 0, C. So let's say in R2. All right, so I take a R2, so I take an object in R2. So let's say this circle here, right? And what I do is I scale it by a factor of C. I scale it by a factor of C. So this is a scaling matrix, which if you multiply by xy, you get cx and cy, right? So it's the same as just multiplying a constant to everything. What do you guys think that the eigenvectors for this should be? Oh my God, this circle looks so ugly. It doesn't matter. I'm not in our school. I don't care. So what do you think? What do you think? Which vectors should remain the same after, at least in terms of direction, which vectors should remain in the same direction after this linear transformation. Anybody want to talk something?
Is it all of them?
All of them. Why is that?
Because, well, depending on whether or not you rotated it, than the original ones, but technically you're just making it bigger, which means that you're multiplying it by a certain length, but it should be the same. It's just
Yes.
by a different scale.
Yes, exactly. Right? So like we can take any vector from here. What did we do in the end? Well, we just take that vector and we multiply by some constant. Right? We did not change the direction in any way. We scaled every single vector out by some factor, but we did not change anything anyway. So in the end, we should expect the eigenvectors to be every single vector. What about the eigenvalue? What should be the eigenvalue? Should be C. Why is that? No, there's no rotation. It is just scaling. So this is the matrix right here. It's just scaling.
Because that's the value we're scaling it by, and that's
the value. Yes. Yes, exactly. Right? Because what eigenvalue is after I plug it in, it does not change direction, but we did not say that it does not change its magnitude. It does not change its form. It does change, right? Direction remains the same, but norm remains different. But what is the scale that the norm is going to change by? Well, the scale of the norm is going to change by a factor of C. Right? So let's confirm that. Let's confirm our hypothesis. Is that true? Well, so first, in order to calculate lambda, we need to compute the determinant of A minus lambda I equals to 0. Right? We need to compute all the solutions for lambda I, or all the solutions for lambda, for which this is true. Well, okay, so this equals to the determinant of C 0, 0, C minus lambda 0, 0, lambda, which equals to 0. So this equals to the determinant of C minus lambda 0, 0, C minus lambda. Right, and the determinant of this is just multiplying it across. So this equals to C minus lambda squared equals to 0. Right, which implies that C lambda equals to C with multiplicity 2 in this case. Right, with multiplicity 2. So this multiplicity here is called the algebraic multiplicity. Oh geez, multiplicity, algebraic multiplicity. In the end, we get lambda equals to C, which we did confirm it. Right, the eigenvalue in this case should just be C. We should just scale everything by C, including the eigenvectors. Okay, so let's compute what are the eigenvectors then. What is the eigenvector? Well, the eigenvectors so what are the eigenvectors? When we're to calculate the eigenvectors, we're looking for all vector v, right, that satisfy this equation here. Correct? Right? Or if we rearrange it a little bit, we have A minus lambda I times V equals to 0. We're looking for all of the v's that satisfy this equation here. Oh, okay. So eigenvectors, right? They just equals to the null space of A minus lambda I. Right? All of the vectors, when you multiply by this matrix, gives you 0. That's the definition of a null space. So let's see what a null space is. Well, A minus lambda I equals to what? Well, lambda in this case equals to C. So it becomes A minus Ci. What is A equals to? Well, this just equals to the 0 matrix. Right? And what is the null space of the 0 matrix? Well, the null space of the matrix is just the entirety of R2. Right? Everything multiplied by the 0 matrix is going to give you 0. So yes, the eigenvectors in this case would just be the entirety of R2, as we expected. Every single vector in R2 does not change direction after we multiply by this matrix. Any questions? So this is a very simple example. I need to get some water. Give me a minute. Oh my god, if I keep on yelling like this, it doesn't take a lot of effort for me to lose my voice. So any questions? So an invertible matrix has no eigenvalues or has trivial eigenvalue. And yeah, that can be up to n amount of eigenvalues, at least one. Well, every single matrix will have exactly n eigenvalues. And the reason is because this lambda is a variable here. This is a variable. This can change, right? So there will be situations where none of these are 0. There will be a situation where none of these are 0, right? So it will have exactly n eigenvalues. Not all n eigenvalues are going to make sense, and not all of them are going to be distinct. In this case, it is not distinct. In this case, the eigenvalue c is repeated twice because this is c minus lambda squared, right? But you will have exactly n eigenvalues. And after this, we're going to do an example where there is no eigenvalues that actually make sense. It will still have 2 eigenvalues, but it will not make much sense. Right? And trivial eigenvalue, there's no such thing as a trivial eigenvalue. Right? And of course, in this case, if I replace c with 1, then it's the same as replacing lambda with 1, right? And if lambda equals to 1, then we didn't really scale it at all. Then the vectors would just remain the same. Well, which makes sense because if we replace c with 1, we just have an identity matrix, and the identity matrix multiplied by any vector would just give you the vector itself back. Okay? I know there is not. Well, it's not necessarily it doesn't make sense. It's just in order to make sense of it, well, I have to talk a little bit about the torus, which I'd assume none of you would rather me do. So this is a scaling matrix. The scaling matrix has eigenvectors everywhere. Okay, and it has two identical eigenvalues, which makes perfect sense. Now let's look at something that makes no perfect sense. Now I said one thing. I said one thing, okay? Every single matrix, every single n by n matrix has exactly n eigenvalues. Right? No, it has not, no. Invertible matrix does not only have one eigenvalue. That is something not true at all. So I said every n by n matrix will have exactly n eigenvalues. They may or may not be distinct. So that means they all have some sort of eigenvector, right? So they all should have some kind of vector that does not change direction after you apply the linear transformation to it. But didn't we already talked about the linear transformation that there is no eigenvector? Does anybody remember which linear transformation that we talked about that has no eigenvectors? Or at least we thought that it has no eigenvector. Anybody remember? We talked about one form of linear transformation that it appears to have no eigenvectors. The triangle rotation, exactly, the rotation matrix. The rotation matrix. The rotation matrix is some beauty. All right, so so A equals to cosine of theta minus sine of theta, sine of theta, cosine of theta. Okay, so right here, this is our beautiful little rotation matrix. So rotation matrix we previously saw with our triangles. Right, if I have a triangle here, after the linear transformation, what do I get? I'm going to rotate everything by, say, pi by 4 angle, right? Pi by 4 radians. This is my linear transformation A. So theta in this case equals to pi by 4. So I rotated everything by 90 degrees, rotated everything by pi by 4 radians. So no vector should remain constant, right? Because I rotated everything. I rotated the entire plane. Oh, I also should include that this is the R2. The rotational matrices for R3 as well, and for any dimension. But in R2, this is that, right? So, but I also said that every single matrix should have eigenvalues, which means they should associate themselves with eigenvectors. So it does contain eigenvectors, but there is no vector that is invariant under rotation. How does that work? Right? So the question is, well, rotation-wise, rotation matrix changes the direction of every vector in R2 except the 0, 0, except the origin. Origin doesn't really have a direction. So what are the eigenvalues and eigenvectors? The result of this is going to be interesting and pretty shocking. And would it depend on theta? The eigenvalue would. The eigenvectors actually do not depend on theta. Very interesting thing. So let's compute it. Let's compute it. Let's compute it. Right? So how do we compute the eigenvectors or the eigenvalues? Well, in order to compute the eigenvalues, we have to solve for lambda for the determinant of A minus lambda I equals to 0. Right? Okay, so this equals to the determinant of, well, cosine of theta minus lambda minus sine of theta, cosine of, sine of theta, and cosine of theta minus lambda. We're looking for this determinant here. Okay, so we take the principal diagonal and subtract the opposite diagonal. So this is cosine minus lambda squared and plus sine squared theta. And we want this to be 0. We want this to be 0. Yeah, not exactly unsolvable. This is just a quadratic equation. So let's split it, see what happens. So cosine minus lambda, the entire thing squared, I get cosine squared theta minus 2 cosine lambda, cosine theta lambda. So 2 lambda cosine theta, right, plus lambda squared, and plus sine squared lambda. This equals to 0. Right? I have cosine squared here, I have sine squared here, add them together, I get 1. So it is 1 minus 2 lambda cosine theta plus lambda squared. This equals to 0. Is there any more simplification we can do? Nope, no more simplification we can do. So from this point on, we have to use our old friend, the quadratic equation. Right? So lambda equals to minus b. So this is b, right? So minus b, which is 2 lambda cosine, no lambda. So 2 cosine of theta. This is our b. Plus or minus the square root of what? B squared minus 4ac. What is b squared? Well, 4 cosine squared theta, that is b squared. Minus 4a, which is 1, c, which is 1, divided by 4a. 4a, whoops, not this a, a. Now 4a, 2a. Quadratic equation difficult. So this equals to 2 cosine of theta plus or minus. I can factor 4 out. So this becomes 4 times cosine squared theta minus 1 over 2. Right? So 2 cosine theta plus or minus, well, square root of 4 is just 2, right? square root of, what is cosine theta minus 1? Well, cosine theta minus 1 is just minus sine square theta, right? And the entire thing over 2. Well, luckily we can cancel the 2 out. So this becomes cosine of theta plus or minus, what is the square root of minus sine squared? Well, I sine theta, which equals to e to the plus or minus I theta. That is the eigenvalue. That is the eigenvalue, right? For some theta, it is not even a real number. It is a complex number. What? What? What did we just do there? What did we just do? I have a rotation matrix in R2, right? It doesn't matter what theta I plug in. These are all real numbers. A rotation matrix in R2, somehow the eigenvalues, so the scaling factor of the vectors, which does not change directions, the scaling factor somehow is a complex number. Isn't that crazy? Well, maybe not. Maybe if you don't like linear algebra, it's not that crazy. But I personally think this is pretty insane, right? It's a complex number. Why is that? So we have our 2 eigenvalues. This is a 2 by 2 matrix. We should have 2 eigenvalues, and indeed, we do have 2 eigenvalues, right? E to the I theta and e to the minus I theta. Okay, so we have 2 eigenvalues that we don't know what to do with. We don't know how we're going to interpret it. Maybe there's something that we can do about. Let's see what we get for eigenvectors. Maybe the eigenvectors will tell us a little bit more. Right? Maybe eigenvectors will tell us a little bit more. Well, yes, C is isomorphic to R2, but if you were talking about C isomorphic to R2, then we actually have a 1 by 1 matrix. Then how do you have 2 eigenvalues? So that is eigenvalues. I ran out of boards for eigenvectors. Well, I can just erase the question. Okay, so let's look at the eigenspace, or the eigenvectors. So look at the eigenvectors. So let's say for lambda equals to e to the I theta. Let's look at the positive case, see what we get. Okay, let's look at the positive case and see what we get. Well, what is A again? What is the eigenvector again? Eigenvectors are all of the V such that A times V equals to lambda times V. Or another way of saying that would be A minus lambda I times V equals to 0. So V equals to, so V is the null space, right? Of A minus lambda I. Okay, let's see what we get. Let's see what we get. So A minus lambda I, what is this equals to? Well, I have A, which is this, right? So I have cosine, I should write it up instead. I need more space. So A minus lambda I equals to, so for A, I have cosine theta minus sine theta, cosine theta, and I have to minus lambda I, So lambda is e to the I theta. So this is going to be e to the I theta. 0, 0, e to the I theta. Okay. So this equals to cosine of theta minus e to the I theta. Sine theta remains unchanged. Sine theta remains unchanged. And cosine of theta minus e to the I theta again. Sure. Okay. Well, what is e to the I theta? E to the I theta is cosine theta plus I sine theta. Right? So I get cosine of theta minus cosine theta plus I sine theta. Right? Minus sine theta still remains. Sine theta still remains. And then I have cosine theta minus cosine theta plus I sine theta. So this equals to, well, cosine and cosine cancel each other out. This is cosine minus cosine. So this is just minus I sine theta minus sine theta, and minus I sine theta. Oh, look at this. This equals to, I can factor out the sine theta from every single part because, again, theta doesn't really matter anymore. So this is the same as just sine theta. I can put a sine theta in front, not that it matters, of minus I, minus 1, 1, and minus I. We're looking at the null space of this. We're looking at the null space of this. So we should do row operations on this, right? Until that we don't have, we should do, well, yeah, we should do row operations on this. So what is this equivalent to? So this is equivalent to, well, if I multiply the bottom by I, right? Sorry, so if I take, yeah, so if I multiply the bottom by I, and, no, what should I do? No, I'm gonna multiply the top by I. Yes, I'm gonna multiply the top by I. I'm gonna use the bottom row to subtract it. So I'm gonna keep the top row unchanged, whereas the bottom row is going to subtract I times the first row. So 1 is gonna subtract minus 1I. So if I multiply by I get 1. So 1 subtract 1 is 0. Right? And if I multiply by I here, I get minus I, and then minus I subtract minus I get 0. So the null space of this of A minus lambda I, right, equals to, well, the second one is going to be a free variable because we only have a single pivot here. So this is going to be a free variable, right? So let's call the second variable T. I don't care. So the second variable is going to be T, right? And the second variable is T. What is the first variable? So if this is T, yes?
So I'm a bit confused how you got from sine theta negative I 1 negative 1 1 and negative I to that negative I negative 1. Oh, did you just reduce it? Never mind. Did you reduce it?
Yes, I row reduce.
Oh, reduced. Okay, sorry.
Yeah, sine, who cares? It's just a constant in that case. Nobody cares.
Are we calculating the determinant?
No, we're trying to calculate the null space of this, right? Because we want to know what the eigenvector is. So in order to know what the eigenvector is, we have to consider the null space of A minus lambda I, right?
Mm-hmm.
So we just calculate what a minus lambda I is. A minus lambda I equals to this, right? And in order to
Okay.
calculate the null space of this, we can just consider the null space of this reduced form.
Okay. Thank you.
Right? Because row reduction does not change the null space. So if I set the second variable to t, so this is going to be t now. So what do we have? We have minus I minus t equals to 0. Sorry, minus I of the first variable, that's called an s, right? Equal minus t equals to 0. So minus I equals to t, minus I of s equals to t. So that means s equals to t minus t over I, right? And if I multiply top and bottom by I get s equals to minus t times I over minus 1, which equals to ti. So this is I times t. So this equals to t of I1, which equals to the span of I1. Ooh, what a eigenvector. What a eigenvector. What the bloody hell just happened? We had an eigenvalue that is complex. We now have an eigenvector that is also complex. This is not even in R2. How do we have an eigenvector that is not even in R2? Our domain. What the bloody hell is happening? This is the type of this. So this is one of these matrices where we think, well, there shouldn't be any eigenvectors or eigenvalues, but it ends up, well, there does exist eigenvectors and eigenvalues, but they're just nonsense that look like this, right? And in order to make sense of them, well, consider a torus, right? Consider, instead of R2 now, let's consider C2, right? Consider C2, consider a torus. If you roll that, oh, obviously there are vectors that does not get changed, namely up and downs do not get changed, right? So what I did on this step, so from this step to this step, I multiply top and bottom by I. If I multiply top and bottom by I get ti on the top, and I get I squared, which is minus 1 on the bottom. Okay. And I mean, this is for e to the I theta. For e to the minus I theta, it'll be pretty much the exact same thing. But instead of minus here, you just have positive. So instead of minus I here, you have positive I. So you have positive I here, and you get 1 I. So it's like reverse. So you have two eigenvectors. One of the eigenvector is 1i, and the other eigenvector is I1 in R2. See, eigenvectors, there are a lot of surprises. There are a lot of surprises. Very interesting things. Very interesting things. Okay? Yes, and the way that you would interpret this would be the idea of a torus, because instead of thinking this in R2 now, you're going to think this in terms of C2, because the elements in the vectors now is in C, so you can think of C2, which we all know what C2 looks like a torus. And now if we take this torus and we give it a spin, or give it some kind of rotation, we can find vectors that, namely, vectors in the cross sections that do not get this rotation switched, right? So that's where the eigenvectors and eigenvalues come from. Look, this thing looks like a Pokemon. So any questions with this? Is there a way to translate complex numbers into R2 since they're isomorphic? Complex numbers into R2 since they're isomorphic. Are they even are they isomorphic? Yes, they are. Yes, they would be isomorphic. Is there a way to go from C to R2? Well, C to R2 is just if you have one C as a plane and then you have one R2, the only difference with the C is you kind of have to fold the plane into a cylinder. It's just, how do you explain it? I don't know. I don't think it translates. I don't think it's just a translation, right? Translation means a single movement. So movement, that's it. No stretching, that's a translation. I don't think the mapping would just simply be a translation from C to R2. It's just, I'm not sure how can I even explain it. I would prefer to keep R2 and C just separate for now. If we want to consider complex numbers, we consider just complex numbers. If we want to consider real numbers, we consider just real numbers. It's probably not a good idea to put the two of them together most of the time. Not all the time. I don't know. I am not very aware of the topology between C and R2. Yeah. If you square it, it will get rid of the I. No, if you square a complex number, it does not get rid of the I. The square of a complex number is still a complex number. So that's this example done. Oh, it is already 4:12. I mean, we still got next week to talk more about eigenvalues. So before we stop, we can talk a little bit about diagonalization, just a tiny little bit about diagonalization. Yeah, your assignment is due next Friday, right? Next Friday, that's when the assignment is due. So we should have plenty more time to talk about eigenvalues next week. Yeah, so for this time, we will just look at. So for now, I'm going to talk a little bit about diagonalization and what it means. So diagonalization. Diagonalization has a few purposes because diagonal matrices. April 3rd. Also next Friday. Yeah, lots of time. So diagonalization has a couple of reasons why we want to diagonalize something. It's because diagonal matrices are very nice to work with. Diagonal matrices are in the form of something like, A1, A2, an, something like that, and then it's 0 everywhere else, right? So you only have numbers on the diagonal, on the principal diagonal. That's what a diagonal matrix is, right? And it is very, very easy to work with. Namely, I mean, if you just multiply two matrices together, B1, B2, all the way to Bn with 0 on top, you multiply these two together, well, you just multiply across. Right, that's like very, very useful. And also the determinant of this, well, if this equals to A, then the determinant of A is literally just the sum of all of these. Sum? No, product. Whoops. You just learn to multiply everything down. So go from 1 to n of AI. Right? But determinant is also very easy to calculate. And also, if you want to raise it to some power, like a to the 100 power, like what Kylie asked you to do inside the assignment, well, that's the same as just raising every single element to the 1000th power. Right? So diagonal matrices have a lot of perks, a lot of very nice properties around them that makes calculation with them so much more easier. Now, then it bears kind of the question, can we do that for every single matrix? Can we do that for every single matrix? Well, the answer is for any square matrix, can you diagonalize it? Yeah. Is it going to look good? Not really. So the intuition behind it, so how are we going to diagonalize stuff? The intuition behind it has something to do with eigenvalues as well, which is why we talked about eigenvalues first, and then we talked about diagonalization. Right? So imagine that I have a, how do I say it? So imagine if I do something like this. I take a matrix A, right? And I multiply it by a bunch of vectors. So I have, I don't know, vector 1, vector 2. So all of these are vectors. Vector 3 to vector n. Right? If I multiply these two together, well, that is going to be A vector 1, A vector 2, A vector 3, and so on, all the way to A vector n. Right? So we're going to use this. But instead of just any regular vectors, instead of just any Vn, what we're going to do is we're going to consider V1, V2, all the way to Vn are, well, linearly independent eigenvectors. So it's not taught in lectures or in tutorial yet, but for now, you just accept it as a fact that two different eigenvalues will have two linearly independent eigenvectors. And if you have multiplicity, you will have the same, so your eigenspace, the basis for the eigenspace would be linearly independent. Okay, so A is an n by n matrix. It has n eigenvectors that are linearly independent from one another. And now I'm going to take A and multiply by all these vectors. What do I get in the end? Can you calculate the determinant of A by the product of the norm of each row? I don't think so. Maybe? I don't know. I need to think about it. So these are eigenvectors, and if I take A and multiply them, well, I get something as a result. So A of V1, V2, all the way to Vn, well, this just equals to lambda V1, lambda V2, all the way to lambda Vn. Right? Because they're all eigenvalues. Oh, and also lambda 1, lambda 2, all the way to lambda n. Right. Every single one of them may have different eigenvalues. Okay. So this is true. So this is true. Now, there's water. I need a bit of water. Okay. On this side, what it actually equals to is it equals to, well, lambda 1, lambda 2, all the way to lambda n, with zeros on either side, multiplied by v1, v2, v3, to vn. Right? Do you have any questions with that? Well, here's one thing. Here's one thing. Every single one of these are linearly independent. Every single one of these are linearly independent. Right? So what we can do is, there's something wrong with this, and to figure out what is something wrong with this. The same though. Is that the same? Why is it column though? Why is it column? Well, I actually forgot how this actually works. This should be true. Oh, of course it should not be true. What am I thinking? It should be the other way around, isn't it? So if I take this and I multiply by this, I only get the first element. No, I want this entire matrix. Yes, that's what the problem is. Okay, never mind. They're not equal to one another. They're not equal to one another. Yes, they are not equal to one another. So this is technically just v1, v2, v3, vn. Yes, I did it backwards. Multiply by lambda 1, lambda 2, lambda n. How stupid am I? Sorry, I did it backwards. That's why the theorem does not work out. I did it backwards. So we want every single one of these vectors to multiply by lambda 1. Well, but every single one of these entries on below the first place is 0. So it is the same as just vector 1 multiplied by lambda 1. And again, we want every single one of the vector 2's to multiply by lambda 2. But it is 0 on top, which means vector 1 multiplied by 0. And it is 0 from this point onwards, means 3 all the way to n would be 0 from this point on. So we have lambda 2 vector 2. And so on, all the way to lambda n vector n. Yes, this is correct. Right? So if we let this vector here, v1, V2, V3, Vn equals to, say, Q. So this is a matrix, right? Every single one of these has a column vector. This is a matrix. If we let this be a matrix, what we have A times Q equals to Q times this diagonal matrix. So I'm going to call this diagonal matrix. So this, I'm going to call this to be capital lambda. Is that capital lambda? I don't remember. I'm going to call this capital lambda. So A times Q equals to Q times lambda. Now, remember that every single one of these eigenvectors are linearly independent, right? Then a matrix that is composed by all of these column linearly independent vectors are going to be invertible because the columns are linearly independent. Therefore, Q inverse does exist. If I multiply both sides by Q inverse, I get Q inverse A Q equals to lambda, or I can get A equals to Q lambda Q inverse, right? Where Q are all of the eigenvectors, and lambda is all of the eigenvalues that is ordered in such a way that lambda 1 corresponds to vector 1, lambda 2 corresponds to vector 2, and so on. So these eigenvector pairs are paired up in this correct order. So we have just generated a diagonal matrix starting from any matrix. Why is this useful? Well, this is useful because now if I do something crazy that I need to do, for example, in stats, it is typical for you to have a matrix and you raise it to some obscene amount of power. Now, if I have A to the power of 100, which is something that I cannot do, right? This is the same as Q lambda Q inverse to the 100, right? So this is Q lambda Q inverse times Q lambda Q inverse times Q lambda Q inverse, and so on. And you can see that this just cancels out, becomes a 1. This just cancels out, becomes a 1. So this in the end just becomes Q lambda to the 100th Q inverse. And lambda to the 100th is a number that is pretty easy to calculate because lambda is a diagonal matrix, right? Lambda is just a diagonal matrix, lambda 1, lambda 2, and so on to lambda n, with zeros everywhere else, right? So lambda to the 100th is also something that is very easy to calculate, would just be lambda 1 to the 100th, lambda 2 to the 100th, all the way to lambda n to the 100th. And from this, what we can also conclude is that in order for p to the power of n to equals to p for any matrix p, in order for any matrix where p to the power of n equals to p, n is any natural number, that implies p can only have eigenvalue 1. Right? This is the only way where if we raise it to the 100th of anything, we get a, or 0. We get itself back. Right? Are those lines supposed to be A? What lines supposed to be A? Or is that the symbol for diagonal matrices? What?
You mixed up the lambda. Like, it's the lambda? Are you drawing lambda, like, to the power of 100?
Yeah, this is lambda to the power 100.
Okay.
Yeah, it doesn't have the line in the middle, so it's not A, it's lambda.
Okay, sorry.
Yeah. This type of matrix has a name, it's called idempotent matrices. So this, they have a name, idempotent matrices. Right. Any matrix where if you raise it to any power, it still equals to itself. That's an idempotent matrix. Okay. So that's like a preview of what diagonalization is going to be, and that is going to conclude today's tutorial. See, I did give you back that 30 minutes, right? So you cannot say that I scammed you 30 minutes. I did give it back. Although I think I've overstayed my welcome on campus. Campus police might be here any moment to kick me out. So is there any questions? If any questions, please speak. And just sit down a bit. I'm not going to be looking at the screen. Ah. Questions? Anything? The only thing I can see right now is the chat scrolling so fast. Oh, never mind. It's like 4 messages. Yes, I am the best TA. Thank you for that. Finals, any updates on that? So I took a sneaky little peek at the current voting situation. I'm not sure if I'm allowed to tell you that. You know what? I don't care. Whatever. It's at the end of the term anyway. It's too late to fire me now. So for now, the two options, which is yes or no, agree or disagree, it is very evenly split right now. All of the people who have taken the survey, it's like a 49 to 51% right now. Now, if it turns out to be a majority no, which is what the situation looks like right now, although with that percentage, it can really shift very quickly, just based on the couple of votes. If the majority says no, then what is going to happen is Kaidi is going to have to report this back to the chair, right? Because the students have rejected the chair's proposal of changing the grading scheme, so I have to report back to the chair, and then the chair will have to contact the dean to come up with another plan, right? Now, another plan is not the same as a different plan, right? Another plan can be the same as the current plan, except there will just be no voting. You get exactly what you have. No, there will not be a second vote. I do not think there will be a second vote. You need to realize that this vote is on March 29th, which is very late. It is incredibly late. Like after that, there is no more time to redesign a plan and have the students vote on it. And with the probability of failing another vote, we don't have the time for that, right? So the only thing that the chair can do at that point is basically just say, okay, this is a plan. You're going to do it. There will be no voting. Because although there is this illusion of vote, we're just going to be democratic, you need a majority of the vote per university policy, the university does not act based on a democratic system, right? If the dean decides to do something to this course, all of the authorities are going to be overridden, and that would just be, all of the votes will be overridden. That'll exactly be what is going to happen to this course, right? Everything is just super late. this entire virus break right now in Europe and in North America is not really helping the case. I mean, if it happened earlier, we would have a lot more time to prepare and to come up with a plan that everybody agrees, right? But it did not happen earlier. It happened very late. The decision to close down everything happened very late. The professors and instructors have no time whatsoever. So yeah, that's the problem.